A creepy screen, turn on the stream. Welcome back. Happy Thursday, everyone.
Happy Thursday.
Yes, yet another day without school for my son.
Oh, pink eye?
Nope. Conferences, parent-teacher conferences. For 3-year-olds. That's not mine, actually. So yeah, he's at home with Daddy right now. Likely not listening to the live stream. I'm guessing they're probably fighting over whether or not he needs to use the potty. That's a very tricky one for him. He really does not like anyone else legislating his bladder. So hopefully none of you have to use the potty. If you do, now is your chance. I'm not going to legislate yours, just other things instead, like homework. So we had a quiz due earlier we can go over. We have homework we can go over. And I just wanted to point out that if I docked you any points on homework 1, Make Friends with SAS, and you want to fix those things to get your points back, that is due by Friday. So let's look at quiz 2, shall we? Go over that real quick. So quiz 2 is reviewing the alternative covariance structure models, broadly construed. So question 1 here. What pattern of variance and covariance would a compound symmetry model predict? Looking for one key word here that starts with a C. What pattern of variance and covariance would a compound symmetry model predict? Maybe your word doesn't start with a C. Maybe you're thinking of a synonym. What'd you put?
Constant?
Constant, that's the word I was thinking of. The same variance over time and the same covariance over time. So how many parameters would it have if there were 4 occasions? 2, yes, and what are they? I didn't ask that. But what are they? Residual variance at level 1 and random intercept variance at level 2. So synonyms for this model then, compound symmetry is otherwise known as what? Skinny jeans. Yes, that's the last question. Correct. Skinny jeans. To someone who's not me, what else would we call this? What is this pattern called if you were to estimate it using least squares instead of residual maximum likelihood? Looking for a word that starts with an A. Actually, it's an acronym.
Not ANOVAs?
That's an ANOVA. Which one is it? There's 3 kinds with respect to different models for the variance. Univariate approach to repeated measures, yes. I would also call this a random intercept only model, as opposed to a random intercept and slopes model. In multi-level terms, that's what folks would call it. But yes, the key idea here is that we have 2 parameters, which means that we have constant variance and covariance. And another way of thinking about that is constant person dependency. There's only one way that there is dependency present in the longitudinal data due to the sampling of multiple occasions from the same person. That one source of dependency is mean differences, is random intercept. That's what this model says. That was one option that we talked about. That was the simplest alternative we would entertain for longitudinal data. The other one, what is the pattern of variance and covariance that an unstructured model would predict? Kind of a trick question in the way it's worded, but not really. Is there a pattern? Non-constant. What kind of not constant? Whatever it wants. So if I have 4 occasions, how many parameters? 10. That comes from 4 variances, 1 for each occasion, and 6 covariances, 1 for each unique pair of occasions. Unstructured means no structure. Gets to be whatever it wants. Synonyms for this. Want to do pants? We'll do pants. What's the synonym for pants for this one? Unstructured goes with? Yeah, sweatpants or athleisure. Something very generous that always fits. Other synonyms for this. This is another kind of ANOVA. Which kind is this one? ANOVA. Yeah, multivariate approach to repeated measures. Yep. And if you took SEM, you also know this idea as what? The saturated model, right? H1. Yep. That's letting the data be whatever it wants. That's the comparison model when you fit your factor models too to see how well it fits in an absolute sense. What kind of data do you have to even try to fit this model? What type of sampling with respect to time? Think about cooperation. Balanced, yeah. We have to have a common set of measurement occasions. Everybody's data has to be able to be described by one common matrix. Otherwise, we don't have this as our answer key, which means we don't have a way to test absolute fit. We don't know what the right answer should be. Next one, if we're going to try to fit something in the middle, something that is more complicated and potentially better fitting than compound symmetry, but less complicated and hopefully as well fitting as unstructured, we might use structures that have an R matrix only, or we might have structures that use G and R. What's the difference? Let me get out my vocabulary spreadsheet here while you're thinking about it. What's the difference? Do you want to review? You're feeling shy or uncertain? Which is it? Or both? What about you? Are you shy or uncertain?
I'm shy.
You're shy? Okay. So like if this were an anonymous survey, you'd fill out the answer? But with the pressure of these like 6 people around you, it's too much? I'm just kidding. No, it's okay. I know some people get really anxious, you know, they don't want to look silly or stupid in front of their friends. I look stupid all the time. It's okay. It's the only way that you can learn is to admit what you don't know, right? So what do you think? What do you think? Since I'm picking on you already, you may as well just go for it.
I was thinking if the G matrix is not used, then the R matrix actually is the total.
Yes, yes, that's exactly right. So in terms of the letters here, here's our review of vocabulary. When we have all of the variability in R, that's total variance and covariance that we're trying to form a pattern for. So for instance, if we fit an AR1 R matrix, then we're saying that the total pattern of correlation across occasions follows an autoregressive structure. Another one you know is toplets, would be another R-only structure. Unstructured is an R-only structure as well as compound symmetry. Alternatively, and this is where compound symmetry can be specified either way, we can use 2 different matrices. We split the model into 2 levels explicitly. G is for level 2 variances. Those are random effect variances. So far we only know intercept. Today we're going to pick up random time slopes as well. So that's the level 2 between sources of inter-individual differences in G. R then must become what's left, which is level 1 within. Residual variances and covariances. It's the E's, it's the deviations around those person means. To get the total put back together again, that's where you have to recombine G and R to get to V, which gives you the total prediction. So if you don't have G, R and V are the same thing. So why would one do it this way? Simplicity. In longitudinal data where you are sampling people, there is often a very strong random intercept. There's a lot of commonality due to existing mean differences between people. That can be responsible for the overwhelming source of the covariance across occasions. So it can be easier to pull that overwhelming source out into G and then try to find a pattern to what's left, the E's. So for instance, one of your homework questions was if you had an AR1 matrix that was R only versus an AR1 matrix in R plus a random intercept in G, and the more complicated one with the random intercept in G fit better, what does it mean? Well, it means that only the pattern of the E's fits the autoregressive correlation, not the total. The total would be part constant covariance due to U with the remainder of the covariance due to E. Same thing would be true with respect to testing homogeneous versus heterogeneous variances. If heterogeneous only fits better after you pull out the random intercept, then you would assume that it's the residual variances that are homogeneous or heterogeneous versus homogeneous. Okay, does that make sense? Okay, yes, sir.
So if I feel like it might have already been explained before, but if we had like deeply nested models, people within classrooms, within schools, within other.
I call those more than 2 levels.
More than 2 levels.
Yeah, sure.
So would those have other matrices to account for those types of variances?
Sorta. G would have more stuff in it.
So
But it's
G
all-
just gets more complex.
Yes. So what would end up happening is, like, G would have, let me see if I can make something that's big enough here in Excel. Like, if this whole thing right here were G, let me make an outline around here. There. If this whole thing were G, like this would be level 3, and then this would be like level 2.
Okay.
So this type of thing where there's like stuff and then zeros elsewhere and then stuff, that's block diagonal. So G just keeps growing, but it doesn't, but there's no other letter that shows up.
Okay.
Yeah. Because then you would have to say that this would be like within level 3, this would be within level 2, and then R would pick up level 1, and it's still V put back together again. It just has a much more complicated structure. Good question. So the compound symmetry model that you know can be specified 2 equivalent ways. One is just to tell it, I want R that's compound symmetry. That's what we've done so far. The alternative is to say, I'm going to end up with a V that's compound symmetry by putting a random intercept in G and a residual variance that is constant with no covariance in R. It's 2 different ways to tell it the same thing. You hear the phrase 6 of one, half dozen of the other? You heard that phrase before? A dozen is 12. Unless it's a baker's dozen, like how many donuts you get in a dozen, then it's 13 for reasons that are unclear. But if you say like 6 of one, half a dozen of the other, it's a phrase that means it's the same thing. Tomato, tomato. So 6 of one, half a dozen of the other. Compound symmetry in R, or random intercept in G, residual variance in R. 2 parameters either way. The latter, random intercept in G, allows you to add other kinds of random effects, such as random slopes that vary across people, such as additional random intercepts for people who are nested in classes, classes that are nested in schools would have another one, and so on and so on. So each level of the model above the first one would have a random intercept at a minimum, and potentially random slopes as well. So adding G to our story here allows us to build into more complicated structures. All right. Any other questions on that? Okay. Then the last one, pants. So we did a couple. Skinny jeans is compound symmetry, sweatpants is unstructured. Tapered jeans that are too skinny at the bottom would be autoregressive, and I said boot cut was Topolitz. Anything with a random intercept is like buying jeans and then taking them to a tailor to get them even better fit. So there's my analogies taken for what they are. So then homework. Let's go over some of those questions. So everybody did fine on the computational stuff. I just wanted to go over why these are the right answers for the drop-down questions here. So which indicates a better fitting model? So we are going next week, I think on Tuesday, to talk about estimation of these models. And so I've just been giving you sort of the summary version of it. But the thing to hang on to is that log likelihood is height, where bigger is better. Certain programs will give you log likelihood, which is the sum across persons of the individual log likelihoods. So how tall each person's data are, given the model parameters. If people are supposed to be independent, then you can add their log likelihoods together. You would multiply likelihoods or add log likelihoods. So if you take a -2 times log likelihood, you're flipping the direction so that then smaller is better. So -2 log likelihood is what we're going to look at in mixed, in SAS, I think in Elmer, in SPSS, and in, no, not Stata. Stata and M+ give log likelihood. So you just have to know which one you're looking at, but smaller is better for -2 log likelihood, bigger is better for regular likelihood. This one, unstructured R, is as good as it can get. It uses all possible parameters to represent variances and covariances that are true to what they are in the data. So -2 log likelihood as an indicator of model goodness will be smallest for this, but not necessarily AIC and BIC. Why not? What's different about AIC and BIC? Sample size for BIC, and for both of them, number of parameters, yes. So AIC and BIC literally start with -2 log likelihood plus some correction that wants to ding you for complicated models that don't fit that much better. So they may not like unstructured, but -2 log likelihood will always be smallest because that's the best you can get. And then valid likelihood ratio test statistics. So looking to make sure that these comparisons follow the rules, the more parsimonious model with fewer parameters is first, because it will fit worse, minus the better fitting model second, so that the difference is positive. The difference has to follow a chi-square distribution, so it has to be positive. So we're looking for things that are nested, but then it's fewer minus more. So taupe H versus taupe, that's backwards. Hey. It's like, yeah, I don't care. HDMI, smart. You know what would be smart is if you didn't shut down in the middle of my lecture. That would be super smart. I don't know why it's angry with me, but I've got your homework and you've seen it before. So taupe H versus taupe. That one is backwards. Make sure this is plugged in. We're on HDMI. Okay, maybe. Come back. Okay, I'm sorry. I didn't mean to yell at you. Don't punish the kids just because you are in a tiff with me. Ah, there we go. Thank you. Okay, that's better. Thank you. Thank you. Promise I'll behave. So H versus not H. That one is going to fit better, which means this value will be smaller than that one. And so it's backwards. AR1 versus CS. Why is that wrong? Why can't you do that one? They're not nested. They're each 2 parameters. Each of them has a variance, and the other one, and then one of them has something that predicts covariance, either an autoregressive pattern or a constant pattern. Taupe 5 versus taupe 4. That one is the same problem as the first one, so that means AR1 versus taupe H is the one that is correct. Now, just because that's correct, do you think that's a good idea? I mean, yeah, I can give you a valid test statistic, but in terms of, okay, then what? What does that tell me? These models differ in 2 distinct ways. The H part, which allows different variances over time, and the correlation pattern. So if the latter one fit better, I don't know why. I can't isolate the source of the betterness. So it's a valid thing, but it's not maybe the most helpful thing. The other ones are looking at the same rule of fewer minus more, but then also what kind of comparisons are allowed when we're using comparison. No, actually not, those ones aren't that. I take that back. Yeah, no it is, NML. What kind of comparisons are allowed in ML versus REML? Anything that involves fixed effects in the means, the comparison has to be ML. So you can do empty versus saturated means, and that would be valid if you're using maximum likelihood. Now, do you have to do a -2 log likelihood difference to answer this question? No. In our class, we are rarely, if ever, going to use regular maximum likelihood. So how would I answer this question? So vocabulary, what's empty means? What's an empty means? One fixed effect, right? What is it? Yep, the grand mean, intercept. Saturated means as many occasions, fixed effects for as many occasions, right? So this comparison is another way of saying, do I have a main effect for time? An omnibus main effect for time? Can you think of another way that I could answer that question? F-test, yeah. Multivariate wall test is what that's called. So we don't need to do -2 log likelihood for comparisons involving the means model most of the time. And if you have a comparison that involves both sides of the model, then it has to be ML as well. And again, this comparison that's the right answer is valid but not terribly useful. Because if it fits better, I don't know if it's the variance part or the means part or both that's making it fit better. So, questions on that? Okay, sure.
If we do the F test and also the ML test, those two results will always give the same answer?
Asymptotically.
Okay.
The difference is degrees of freedom, right? So F has denominator degrees of freedom, these tests don't. So if you have a big enough sample, they do. In practice, they will disagree to some extent. I have never seen the case where the conclusion would change. So maybe the exact p-value might be different, but they should point you in the same direction. All right, let's look at the other ones then. So we talked about this then. R only AR1 versus R only ARH1. Those differ in their what? Variance or correlation patterns? Variance, right? Yeah, say it aloud. Don't be shy. Yeah, no one's allowed to be shy in here. It's the new rule. Variance. Okay, so now is it total or is it residual? And this is where it's tricky because it's R only, right? Which means total because there's no G. But what is it called in SAS's output? Residual. It uses the word residual even when it doesn't mean residual. You know why? Job security. Because if you figure this stuff out, someone will pay you. It is in their best interest to protect their market share, to keep it hard to understand, so they're valuable, right? If this were super easy, everybody could do it, what good would that do? Now, I'm being a little cynical, but not really. So then, R only AR1 plus random intercept plus AR1, these differ in their pattern of correlation. So the ladder model, random intercept plus AR1, says there's two sources of correlation. There's constant, that's the random intercept part. So no matter how far apart in time the observations are, there's at least some covariance because of the random intercept. Beyond that, the residual E part has a correlation pattern that follows AR1. So residual correlation is autoregressive. If we have a random intercept in G, what is true about the diagonal elements? R plus G is V. So V always has to be the biggest. Which of these you can't estimate? So the number in parentheses refers to the number of bands in the matrix. So like UN5 means I have 1 diagonal and 4 off diagonals. That one's okay. UN4, given 5 occasions, that one's okay. Although it wouldn't make a lot of sense because that one would say that the last pair doesn't have any covariance at all, which is unrealistic in longitudinal data. Ri plus UN5, that's the broken one. Because you can't have the whole matrix be estimated and then one more thing. That is, SEM people, what would we call that? When you have more parameters than you have pieces of data to estimate them with? Under-identified. Yep, that's what this is. And R1 plus UN4 is just identified. It will fit the same as UN5. Just a different way of getting to the same place. And then last but not least, what are the parameters in a random intercept plus Topolitz heterogeneous 4? All right, so all of them have random intercept. We have 6 occasions, and we have an H. So that means that we have to have 6 residual variances. Then the last part here, what does the 4 mean? Now you would think that that means 4 lagged covariances, but it doesn't. It means 3. It's because it's counting the diagonal. So that one is tricky for the Topolitzes. All right. Any other questions about this homework? No. All right, then I will shut it down and we can move on to new stuff. Okay. So as a way of reviewing what we talked about last time, I'd like to dive into our example that goes with this. So example 5. Okay. So this is from chapter 5 in the book. This is fake data from a sample of 25 persons. It is balanced for right now. It's easier to start with the simpler cases and then work our way up to the more complicated ones. I think everything you're going to see this semester is balanced, but the rest of the book tackles various types of unbalanced. So I'm reading my data into SAS here, and I'm making a new variable that I'm calling time. So in the code that you're going to see, there's going to be 2 different variables referred to that keep track of time. There's going to be time and there's going to be wave. Wave is 1, 2, 3, 4. Now why can't I take wave and put it in the model and estimate a slope for wave if wave is 1, 2, 3, 4? First off, can I do that? I could, right? It'd be weird, but I could do it. Like SAS would let me. It would spit out numbers back at me. Now you're shaking your head. Why do you say no to that? Because I think you're onto something. It's not that it's not identified. It's that there's a model parameter that would not be meaningful. So if I have wave 1, 2, 3, 4, and I put that in as a predictor, where I want to have a slope, a line through 1, 2, 3, 4. Where's my intercept? Yeah, I gotta fix it so that time 0 is somewhere in there. Otherwise, my intercept refers to the occasion before I started collecting data. However long ago that was. So time is going to go into the model anytime that we want a slope. Wave is going to go into the model whenever we want to just estimate a mean for each wave, or when we need to identify the dimensions of the R matrix. So for instance here, my first model, because I have balanced data and I only have 4 occasions, I have enough information to estimate what I would call the answer key on both sides. So saturated means each occasion gets its own mean, so I have 4 occasions, that's going to be 4 parameters, 1 intercept and 3 differences. And on the variance side, I have everything in R. So the R matrix is controlled by the repeated line. I am telling it what is being repeated across person IDs, that's my subject for level 2, is wave. Now if I don't have wave here on the repeated line, then it doesn't know which row of the data set to put into which row of the matrix. If I had somebody who had wave 1, 2, 4, like there was no row 3 for them, it would take 4 and stick it in row 3 because it doesn't understand. So having wave here makes sure that each row goes into the right place in the event of any missing data. So on the class statement are my 2 nesting variables. Person ID separates level 2 units. Wave distinguishes level 1 units. Cove test is an option that gives me standard errors for the covariance parameters. No CL print suppresses extraneous output related to the class statement. IC gives me a table of information criteria, so AIC, BIC, stuff like that. And method equals REML is the default, but I put it here to be explicit that that's the method of estimation we're using, is residual maximum likelihood as opposed to regular flavor maximum likelihood. So wave being in the model to predict my outcome, the fact that it's on the class statement means that I'm not asking for a slope. Wave is treated as a factor variable. It's going to dummy code and make 3 contrasts that will differentiate my 4 waves. So 3 contrasts that will differentiate my 4 waves, that gives me a saturated means model. That's my ANOVA model. That's what repeated measures ANOVA does for you. It's the same thing. It's the same idea. Exact same thing. And then down here, repeated wave, type equals UN gives me what? Unstructured. Everything gets to be what it wants. So the means get to be what they want. The variances get to be what they want. The covariances get to be what they want. That really is your saturated model in SEM. That's your H1, where everything gets to be what it wants. Just identified. Why am I fitting it? Because this is the answer key. This is going to give me the pattern that subsequent models are going to try to approximate more parsimoniously, but hopefully as well-fitting. Sure.
So for the model option, if we have another variable as wave 1, which has the same value as wave, but we treat it as continuous and put it there, not like outcome equals wave 1.
Mm-hmm.
That model, so for the mean structure, that model becomes like linear and it's not the same as this one.
Exactly.
Okay.
Yep. And just to show you that is coming. Yeah. That's coming. Yep. Instead of calling it wave 1, I called it time, but otherwise what you said is exactly right. So yes, in this present case, going back, the fact that wave is on the class statement means that it's being treated as a categorical variable. So it's a grouping variable. And then because it's on the class statement, I can ask SAS to spit out means for it. So LS means least squares means. So it can give me what the model says the predicted mean should be at each occasion. Other questions? All right, so then going through the output here, R matrix, everything's in R right now. Here's my pattern. What do you think about the variances on the diagonal there? Same or different across time? Different, yeah. Different, like random, or different in a pattern? Increasing, yeah. People are spreading out. Correlation pattern over time. Constant or some sort of not constant? I'll vote for some sort of not constant. Yeah, not constant. So right away, I know two things. I need a model that allows the variance to grow over time. That means having a random intercept only can't possibly be right, right? Because random intercept says same variance over time. And with respect to the correlation pattern over time, I need a model that allows it to change over time. And for that reason, also, random intercept only cannot possibly be right. Under covariance parameter estimates, this table, which SAS calls cov-parms, will always have every parameter that is part of your model for the variance. UN11 is the label for the first one. Isn't that a terribly helpful label? What is that? Well, let me decode it for you. UN refers to the unstructured matrix, that's R. 1, 1, can you guess? Row column, yeah. Row 1, column 1. So asking it to print R just basically takes that table and puts it in a way that's easier to read it. This covariance parameter estimates table comes with standard errors, z statistics, and probability that, of a p-value that goes with this z. That's what this cove test option added. But I'm here to tell you, this pz column right here, you are never, ever, ever, ever allowed to look at it. Pretend it's not there. Now, Ori's looking at me like, here's why. This is a Wald test. It's the idea that we can take the estimate of our variance, go 2 standard errors on either side, right? And we have some kind of normal sampling distribution that forms that z. But what's the smallest number of variance can be? 0, right? So if you picture this 2-sided sampling distribution, as it gets closer and closer to 0, it's going to bump up against a wall, right? Where the negative part would go, and it has to stop. And the closer you get to 0, the more you want to look at this p-value to see that it's different than 0. So in general, when you have a parameter whose sampling distribution is going to go up against a wall of some kind, then a Wald test can't be right. So this is what's known as the boundary problem in statistics. Whenever you have a parameter where 0 is a boundary, it can't be the null hypothesis of a traditional Wald test. It doesn't work. So all decisions that we will make with respect to these covariance parameters, and by covariance parameters it means variance and covariance parameters, we will make with likelihood ratio tests. -2 log likelihood differences. And this is why, like James, I know your name, he was asking me how to get these columns in Elmer, was it? Or
yeah.
LME for?
Or NLME.
NLME. And so I asked my R guru, one of the other professors here, Brandon LeBeau, and he said, the guy who wrote the package doesn't believe in these, so you can't have them. That was his answer. Okay, that's but this is why, right? They can't be right. So they might accidentally be right if the thing is far enough away from 0 that the confidence interval doesn't include 0. But the situations in which you'd want to check them, they're going to be really close to 0. So don't pay these any attention. All right. So here's my -2 res log likelihood. By the way, if you're ever not sure, if you're in ML or REML for your estimator, check this number right here, this word, excuse me. Res log likelihood means it's REML. The res will be missing if you're in ML. So this table is here, but we don't need to use it for anything right now because we're not doing any model comparisons. We're just looking at what the parameter estimates are to get a sense of the patterns. So this null model likelihood ratio test, that thing that it's printing is not terribly helpful. It prints it for you anyway. 9 degrees of freedom means besides just regular E variance, there's 9 other parameters that make up the model for the variance. That's because we have an unstructured matrix with 4 occasions, which means 4 variances, 6 covariances, that's 10. 10 minus E at a minimum would be 9. So this is just telling you that, hey, could you just use regression for this and call it good? No, that's what this means. Now what to do instead, it's not telling you, but that's what that phi value means. We do not have independent data. That's what. Solution for fixed effects then helps us understand the coding scheme that SAS came up with for our categorical predictor of wave. By default, the last category, so the highest numerically or the last alphabetically is the reference. That's why you get 0 here and ... Don't be afraid when you see this. This is not bad. This is bad when you see it in a variance table. If you get a variance that's 0 with ... that means your model is broken. Non-positive definite. Do not pass go. Do not collect $200. That's what it means if it's in a variance table. But the fact that it's in the fixed effects table, the model for the means, is just telling you that wave 4 is your intercept. So in this outcome, the mean at wave 4 is 15. These are contrasts that compare wave 4 to each of the other waves. So wave 1 was 5 lower, wave 2 was 3 lower, wave 3 was 1 lower. And the combination of these 3 contrasts, these 3 univariate wall tests, the combination of testing whether they're different than 0 is the next table right here. This type 3 test of fixed effects that has 3 degrees of freedom in the numerator. Denominator is 24 degrees of freedom. This is our omnibus main effective time. This is your repeated measures main effective time. The multivariate version. The next table then takes those contrasts and adds them to the reference so that you can see what the means actually were. And I stuck those into Excel and made some pictures. So a couple things I want to point out. Means, do they look like they're the same over time or different? Different, right? People are growing. Here's my growth curves. Excuse me, plot of individual trajectories. What about the standard error of the mean? Growing, because people are spreading themselves out. So that points to a heterogeneous variance model of some kind. Here's the trajectory on average. Sometimes, if you have missing data, what you will find is that if you fit this model and look at those means, they will not match the means from your data. The reason is that these are estimated means. They're estimated as if your data were complete. They're trying to recreate what the parameters would be for the means at each occasion if you have complete data. If you don't have complete data, then the means you get from your data are going to be different. They're under a different mechanism, completely at random versus missing at random here. These are the means that your model is going to try to fit. When you try to draw a line through this, these are the means that it's looking for. So to me, if you're going to have a table of means, it's these ones that are relevant. They're the estimated means that the model's trying to fit, not the raw data means. They'll only differ in the event of missing data. So here's a plot of the variances by wave. You can see that those increase as well. So ideally then, you would run this type of model, this answer key model, look at these patterns, and then try to decide what kind of pattern it is. What type of functional form would we need to describe the change in the mean over time and the change in the variance? Now in this case, the red line looks pretty linear, right? That's because we're only talking about linear for right now, but we'll get some bendy shapes coming up later. Blue line, increasing, but increasing linearly. No? What do you think, Isma?
Linear equations are not good enough to explain these changes, so we will need some polynomial.
Some kind of polynomial? Yep. That's a dead giveaway for a random linear model. So we haven't seen this yet, but what the random linear time model predicts is quadratically changing variance across time. And that was indeed what generated these data. If you're in a situation where you can't do the unstructured R matrix because you have too many occasions or unbalanced data or what have you, this is the alternative that I would do. I would always try to get the model for the means, get the mean in each occasion just to see what kind of trajectory you're going to need and fit it with the random intercept only. That way you can get at least the front part there, the means part. All right. So then what we talked about last time is where we would start in terms of the simplest possible model. So this will work no matter what kind of data you have, balanced or unbalanced. Empty means random intercept. So in terms of notation, here's my little equation box here on the right. Level 1 model, y for each time for each individual, is a function of an individual intercept placeholder, that's beta 0I, plus a time-specific and person-specific residual. Beta 0I then, how each person gets their intercept, is a combination of a fixed part and a random part. Gamma 00 is my fixed intercept. In this case, that's the grand mean. It's the mean of the person means, more specifically. U0 is the random intercept. It's the deviation for person I. And if you fill in the beta 0 placeholder, you get to the composite equation here, fixed part, random part, plus time-specific residual. So in terms of terminology, I would call this a random intercept model. If I were listing everything that's in the model, I would say it has a fixed intercept and a random intercept. But the way that random effects work is that they are always phrased as deviations from a fixed effect. So it is assumed if you have a random effect, you have the fixed effect that goes with it. So I don't have to mention that I have a fixed intercept. It's implied by the fact that I also have a random intercept deviation from the fixed effect. Does that make sense? Okay. In SAS, though, fixed intercepts are included by default. You do not have to write them. That is pretty much almost always the case in linear models. But the random intercept is not included by default. So let's go over these two lines and make sure that you understand what you are asking for. First line, random. That's how you tell it what kind of G matrix you want. How is the G matrix going to be organized? By person. So James, to answer your question, if people were nested in schools, you would have another random line where the ID would be school. And then this one would have to be person within school. And then you'd have a G matrix that has sort of two chunks in it, one for schools and one for people.
Okay.
So I'm asking for a random intercept. So my G matrix is just a scalar. It's going to have one thing in it, the intercept variance, which is going to be level random intercept, 1 or 2? 2. Between or within? Between people, yep. I am asking it to print a bunch of stuff for pedagogical reasons. You don't have to ask it to print all this if you don't want to, but I'm asking for G. So that's my level 2 matrix of random effects, variances, and covariances. I'm asking for V. What's V? Total. G and R put back together again. The total prediction for the data. V core is the correlation version of V. Type equals UN. So I want you to highlight this here, because you know what? Type equals UN on your random lines forever and ever, amen. Say it with me. Type equals UN forever and ever, amen. I'm not kidding. Some of the dumbest reviewer complaints I've ever had to deal with is people saying, well, why did you think on UN it should be AR1?
Does it matter?
No. Right now it doesn't matter. There's one thing in it. I can't have a type with one thing. I have a number. But when I have more than one thing, that's where this matters. And so I just leave it here all the time so that I don't have to worry about changing it. But what this means is that your G matrix gets to be whatever it wants. If I put in a random intercept, its variance should be estimated whatever it wants to be. If I put in a random slope, that's coming next, then its slope variance gets to be whatever it wants to. It makes no sense to pattern it. There are only very specific cases in which you're trying to trick SAS into doing something it wasn't designed to do, where you don't have intercept here, that a different structure might make more sense. But the situations that you will likely see at first, type equals UN for your random line forever and ever, amen. Now where this gets confusing is that there's this other line here which is repeated. And it has its own type, which is different. So repeated goes with R, which is level 1, which is within or between, within. Okay, different matrix, different concern here. Now we're talking about within person residuals. So we're defining R to have as many rows and columns as we have waves. If we have incomplete data, then people who have fewer than 4 occasions will have an R matrix that's smaller. If they have 3 occasions, it would be a 3 by 3 instead of a 4 by 4. No worries. I'm asking it to print R so that we can see what it looks like, and type equals VC is actually the default for a repeated line. So if you forget this whole line, this is what you get anyway. VC stands for variance components. It's an independence structure. It's what you would call a regression model E. Constant variance across all observations, no covariance whatsoever. And the R matrix is per person. So now, next to that, you can see the estimates for this particular data set. So it's printing the R matrix for person 1. By default, it prints it for the first person. You can ask for others, but in this case, it doesn't matter. Everybody has the same set of observations. So on the diagonal, what's that 7? Sigma squared. That's E variance at level 1. The off diagonal is blank because it means 0. This is saying the E's are unrelated. The only reason that they would have been related is now over here in G. And this 2.88 number, what's that thing? Random intercept variance, yes. So if I take this 2.88 and I add it everywhere in this matrix of R here, I get V. This is my compound symmetry structure in V. Constant variance, constant covariance. The correlation version then says that the constant correlation across occasions from the same person is 0.29. That has a special name. ICC, yeah. So 29% of the variation in this outcome is between or within persons? Between. Is cross-sectional or longitudinal? Cross-sectional. 29% of the variance is due to existing person mean differences. So the two parameters that are being estimated in my model for the variance that make up these patterns then, the 7 and the 2.8, UN11 refers to row 1, column 1 of the unstructured G matrix. That's another way of saying random intercept variance. The order of the G matrix is always the order in which you write things on the random line. I also asked it to print G with a label so that you can see what the 2.88 refers to. And then wave is how the R matrix is structured, which is why the 7 shows up there, which indicates residual E variance at level 1. Relative to a model without a random intercept variance, this null model likelihood ratio test gives me the difference in fit. So the test statistic then, the chi-square, that is the difference in -2 log likelihood. So you can write that a couple different ways. Sometimes you'll see it in articles as just like a chi-square symbol. Let me see if I can write this thing. Like you can just say chi-square with 1 degree of freedom equals 9 point whatever, 9.79. What I like to do is write it more explicitly as a -2 triangle for difference. -2 log likelihood difference for 1 degree of freedom. You can also write it, I've seen this before, chi-square with a little 1 subscript like that for degrees of freedom. So any of these works. So the fact that it's significant means that the model with the random intercept variance fits better. In other words, this intra-class correlation of 0.29 that reflects the contribution of that random intercept variance is significantly higher than 0. That's what the chi-square test is telling us. Last but not least, gamma 0, 0, my fixed intercept is 12. So if I were writing a method section, which or a result section, which every chapter in my book has a result section at the back of it for all of the examples, this would be 1 line. An empty means random intercept model was initially used to partition the variability in this outcome and revealed an intra-class correlation of 0.29. Thus, comma, I like thus a lot to start sentences. Thus, 29% of the total variation was between persons, due to mean differences, due to random intercept, however you want to phrase it. That's the only reason you fit this model. You say that, you move on. So now let's start pattern hunting. Why am I fitting a linear model for time? Because I made this picture and I think it looks linear. If the picture looked like something else, I might go a different route. But we're starting with linear because it's easiest, and then we can work on adding more complicated types of trajectories. So I'm at equation 5.3. Level 1 model now has a new term in it, beta 1. That is a placeholder for how each person is going to get a linear time slope. So beta 1i for each person, time gets a TI because it's per time per individual. More generally, any variable that shows up in this level 1 equation gets a TI. If it's a variable that doesn't vary over time, it doesn't go there. It goes in level 2 instead. Because I have 2 betas in level 1, I've got 2 beta equations in level 2. Each of them starts with a fixed effect. So gamma 0, 0 was my fixed intercept. It used to be the grand mean. Now it's going to be the expected mean at time 0, which is wave 1. Likewise, I have gamma 1, 0. That's my fixed time slope. It's 1, 0 because it's referring to beta 1. And it's the 0 because it's the first way of making a prediction for beta 1. It's the first entry into this level 2 equation. However, I don't have anything else in my beta 1 level 2 equation. So that means I am predicting everybody has the same rate of change given by the fixed time slope gamma 1, 0. Fixed means everybody gets the same. It doesn't yet have a random part that makes everybody's slope different. And so note wave versus time in the syntax. Wave is a categorical variable. It's an ID variable. So it shows up on class and repeated to structure the R matrix. Time, because it's not on the class statement, is treated as a continuous predictor. Therefore, I am getting a time slope. If I wanted to estimate a bendy slope instead of a linear slope, like a polynomial, can you guess what else I would put in here? Time squared, yeah. But right now it's linear because that's all I've asked for. Time squared will be chapter 6. The model for the variance is exactly the same. I have a random intercept in G, a residual that's constant over time, no covariance in R. And then the last 4 statements, just me asking for what the model predicts the intercept to be at each occasion. So you can think of it as a conditional intercept or a predicted outcome or an expected outcome. All of those words mean the same thing in this context. And so I'm literally just filling in the equation here for the fixed effects. To get to what the intercept is at time 0, I need 1 fixed intercept, and I need a 0 where time goes in the equation to multiply the fixed slope. The other lines then substitute the value for the time predictor for which I want a predicted outcome. The estimate statements do not have anything filled in for the random effects. So it's not a person-specific prediction, it's average for the sample. Okay, questions on the code? All right. So is time a level 1 predictor or a level 2 predictor? Level 1. Level 1, yeah, right there, right? Therefore, is it going to predict the E variance that's at level 1, 2, or U variance that's not at the same level? E, yeah. So we can quantify, in addition to whether or not the fixed slope for time is significant, we can quantify how much variance we've explained by adding it to the model. So my residual variance in my R matrix used to be 7, now it's down to 2. So if I have what it was, 7, minus what it is, 2, divided by what it was, 7, that's where I get the 69% reduction. These are the same numbers that were in the PowerPoint slides. So I have an R square of 69%, or 0.69. Now, can I just say that? Model R square is 0.69. What do you think? Nope, can't say that exactly. Need to be more specific. I've explained 69% of what exactly? The level 1 residual. Now, how much of the total variance was due to level 1 residual in the first place? Yeah, it was, the ICC was 0.29, so it would be 71. So of the 71% of the variance that was over time, putting in a fixed effect of time explains 69% of that 71%. And because the residual variance went down, random intercept variance in G at level 2 has to go up. It used to be 2.88, now it's up to 4. That's because of the correction factor. There's less of what the model perceives to be noise at level 1, and so it is undercorrecting it relative to what it did in the empty model. Doesn't mean anything, doesn't mean you made it worse. It's just what happens. All right, how are we doing? Do you have it in you to look at just one more model? Adding a random slope? The thing you've been waiting for? So these are the predicted means here on the next page. We'll look at just the solution for fixed effects real quick. So 10, that's my fixed intercept. That is the model predicted mean where time equals 0. Given the way I coded time, that's at wave 1. So this is not the mean at wave 1. This is the model predicted mean. It's the mean according to the line I drew. The fixed effective time is 1.7. So for every 1 unit time change in time, my outcome goes up by 1.7. Now, if you were writing this in practice, 1 unit change in time is not helpful. You would want to substitute in for every year, for every day, for every month, whatever time is, use the scale. Now, in this case, can the effective time be positive or negative? In general, could it? Could they get worse instead of better? Sure. So a null hypothesis of 0, perfectly reasonable. That means we can stare at this p-value. This is our univariate wald test. This is the same p-value you're used to staring at in regression. It's totally fine because 0 is not on the boundary of what the fixed slope can be. So yes, there's a significant fixed effective time. It's significantly different than 0. The effect size that goes with it is that it explains 69% of the model's level 1 residual variance. If you wanted to, you could also take this t value and convert it into another type of effect size, such as a d, or an r, or a g, or an h, or whatever letter you feel like. I have to ask Ariel about that. But point being, there are conversion formulas by which you can convert t's into other things, if you don't want to do pseudo r-square. Okay. Last model then, we'll get this started and then revisit it on Tuesday. Random linear time. So spot the change in the code. What makes it different than the previous model? Time. Time where? Yeah, random line. Now there are 2 things that vary randomly across persons, their intercept and their time slope. Now it matters that we have type equals un. It's a 2 by 2 matrix at level 2. Where does that change show up in my equation? What's new? U1, there it is. So just as U0 is how far off your intercept is from the average intercept, U1 is how far off your slope is from the mean slope. So looking at our new model for the variance that we've added a random time slope to, our matrix is the same structure as before. That's level 1. We are saying E variance is constant over time, no covariance. The only reason there would have been a covariance is now over here in G. G is 2 by 2. We have my random intercept variance and we have my random time slope variance. And because we added a random time slope variance, we also added a covariance between the two. So when I say on your random line type equals UN forever, endeavor, amen, it's that these 3 things get to be whatever they want. It makes no sense whatsoever to say that your random intercepts and slopes should have an AR1 structure or topolets or anything else. It makes no sense. The default is that the variances get to be whatever they want, but there's no covariance. And I will argue with people about this too. In other people's multi-level modeling books, there's a whole section called "Don't force the covariance to be 0." Generally speaking, if you have random effects that come from the same sampling unit, like the intercept and slope come from the same person, it gets to be related because it came from the same person. So type equals U and make sure that the covariances are added as well as the variances. Here's the correlation version of the G matrix that I also asked for. That gives the correlation between the intercepts and slopes. So where you are at time 0 is mostly uncorrelated with how you change over time in this case. And that builds a V matrix that's at the bottom here when we put G and R back together again. And lo and behold, look what happened to my predicted variances over time. They grow! Look what happens to my covariances over time. They change! It's beautiful. So now we have a new pattern. Where did that pattern come from? We'll talk about that next time. It's magic. How do we know if that new term helped? Here's my new term, UN22. Can I say it's significant by staring at this? No! 10 people in the world will yell at you, just in case one of them is your reviewers. No, likelihood ratio test. So we'll talk more about the details of that as well. All right. Cool, huh? Questions?
There a 5.4 model? You just jump by 5.3 to 5.
This is 5.5. 5.4. Oh, I think I just I think I mislabeled it. 5.4 must have been something else in the book that I didn't need. So the 5.5 goes with the equation in the book. So this is following chapter 5. So I built this handout out of it, so. Yep, 5.4 was something else. So I'm going to put up a new homework for you to work on that just gets you used to navigating this type of output for these sorts of models, and asking you to do some comparisons of what the results look like in ML versus RML. So I will send out an email when that is ready. It will be due next Friday. All right.
So I
Yeah.
have a question generally.
Mhm.
So in linear mixed model, we work on the variance covariance structure and also the mean structure.
Mhm.
And from the, I'm not sure whether like meta-analysis standpoint, like if we do the experiment, like replicate the experiment across like different samples,
Mhm.
which part is more stable?
The means part of the variance part?
Yeah, like because maybe different samples will support different like assumptions of the covariance structure. Maybe in like certain sample it's like compound symmetry. The other sample maybe like I'm not sure like other types, and it gives like inconsistency. So and also I think the same thing happened in the mean structure. So based on your experience, like which part tends to be like varying more across samples?
It takes more people to nail down the variance structure than it does to nail down the mean structure. So to the extent that you're working with small samples, what you get back from the variance model could have a lot more noise to it than what you get back from the means model. In particular, variances tend to be underestimated in smaller samples, like random slopes. Random slope variances are harder to find if you have fewer people, because people is power with respect to random effects, whereas time is level 1. So in this case, you have somewhere between 100 and 25 as your power at level 1 based on the intra-class correlation, whereas your power at level 2 is 25. So there'd be more chance to have different results across multiple samples of 25 in the level 2 terms, such as the random effects, than the level 1 terms, such as the fixed effective time.
So the highest levels, the sample size in the highest level decides the power that
The power for things at its level.
okay.
So you really have to think of it as two models at the same time. With respect to anything at level 2, which includes random effect variances as well as person level predictors, my power is based of 25 people. With respect to anything at level 1, it would be number of occasions times number of people. So 100 here if there was no interclass correlation and they were independent. If it was an interclass correlation of 1 and they were completely dependent, then level 1 power would be 25 also. Somewhere between 100 and 25 is your power for level 1, just based on how much dependency there is. So you got to think of both in sample size planning. Other questions? All right, then we're done for now. I will see you next week. Have a good weekend. Let me know if you need anything.